We know that vectors are physical quantities which have got both magnitude and direction, right? And hence addition of vectors or subtraction of vectors becomes slightly complex. You cannot simply add the magnitude. For example, if you have got a force of F1 of 5 Newton acting on an object, and F2 is equal to 2 Newton acting on the same object, we can't simply say that the total force acting on this is 7 Newton, right? Because the direction of these two forces could be different, and when directions are different, you cannot simply add directions or subtract direction. Hence, we use a method which is known as the graphical method for addition of vectors. Let me first give an example. Right? Supposing you have an object, a block over here, and there's a force of 5 Newton acting on this and 2 Newton acting on this. Since these two forces are in the same direction, we can say that the total force acting on this is 7 Newton in this direction. But as I said earlier, we have situations wherein maybe two forces are acting on this, 5 Newton in this direction and 2 Newton in this direction. Now these two forces have different direction, and therefore we can't simply add and say 7 Newton is the force acting, the net force acting on this particular object. In such a case, we use a graphical method. In this video, I'm going to talk about the graphical method of addition of vectors, and in a subsequent video I'll talk about how vectors can be added by an analytical method. Okay, so what we do in such a case is that we first begin by taking a scale. We say 1 centimeter is equal to 1 Newton, say for example. And then I draw these two vectors, right? For example, this is 5 Newton, so I'll maintain the direction. So I'll draw a line 5 centimeter long in this direction, right? Which will represent the force of 5 Newton acting on this particular object. So line of 5 centimeter long approximately, right? This is the starting point, and this is the force of 5 Newton acting in this direction. And then I'll draw a vector which represents 2 Newton. So line vertically down, right, of 2 centimeter length. So this is representing vector 2 Newton. Let us call this as vector F1, and this is F2. Right? What we have done is we have shown the effect of these two forces. When I drew this line, what I meant was that there's a force of 5 Newton acting on this, and the effect of this is line, meaning that this force has a tendency to take this object in this particular direction. So this line represents the effect of this particular force. And after considering the effect of force F1, I add to that the effect of force F2. So I draw a line vertically downwards, meaning that this particular force now is taking this object in the downward direction, even though actually it may not be able to do so. But these two lines, one after the other, represent the effect of the two forces, right? So this is the starting point, this is the finish point, and therefore the line which joins these two, right? The line which joins these two will represent the resultant of these two forces. So I'll draw it this, right? And this represents the resultant or the net effect of these two forces, right? If I measure the length of this particular line, let us say what is the length of this line coming out to be? It is coming out to be around 5.2 centimeter, right? 5.2 centimeter. So the net effect would be approximately 5.2 Newton in this particular direction. I can also measure this particular angle. Let us call this angle as theta. And if I know this angle theta, because I know the direction of the force F1, I would also be able to find out theta. And then I would know this resultant, both magnitude as well as direction, right? I would know the magnitude is 5.2 Newton and the angle that it makes with the first vector is theta. Thus, I completely know the resultant effect of these two particular forces. This is how we add vectors, right? And this method that we have used is known as the triangle method of addition of vectors, because we form a triangle when we use the graphical method, right? The question that you may have in mind is that we took 5 Newton force first and then we took 2 Newton force. What would happen if we reverse the sequence? It turns out the result would be the same. We would still get the same resultant. Let us try this out. Let us first take the force of 2 Newton. Right? So first I will draw, this is F2 now. F2 is equal to 2 Newton. And then I will draw approximately, I'll get this, and I will draw a line 5 centimeter long approximately, right? So this will give me the force F1, which is 5 Newton, and then I join the starting point and the finish point, right? And that will represent the resultant. Right? This is R. And you can see over here, that this R and this R nearly are in the same direction and nearly have the same magnitude. There is a slight difference because I have not drawn it exactly to scale. But we get the same resultant. So the order, this order of sequence is not important. So which we state as A plus B. If I add vector A to vector B is same as adding vector B to vector A. Right? And this means that vector addition is commutative in nature. The sequence in which we add the vectors does not matter. Right? This is one of the properties of addition of vectors, that the addition is commutative. And another point that I want to mention over here is that R depends, that means the resultant R that we found out depends on angle between the two vectors. Meaning that if the angle between the two vectors changes, the resultant would change. Let us try to see this with an example. Once again, we will take this, right? Now I will not draw it to scale, I will simply try to draw it freehand. Right? Let us say this is the first vector F1, right? This is vector F1, right? I have drawn it to 5 centimeter length line. And let us say the angle between the first vector and the second vector changes. So instead of this line coming vertically down, let us say it goes at an angle, right? Magnitude is same, 2 newtons, but it goes down like this, 2 Newton F2. And you can very clearly see that the length of this line would now decrease because the angle over here has changed, and this would be R, and it would be different from 5.2 Newton. So if this angle changes, the resultant changes. If this 2 Newton force acts more, goes in this particular direction, the resultant would change further. So resultant R depends not only on the two vectors but the angle between them. Right? That's the point that I wanted to share with you over here. Next, I want to talk about the method of parallelogram. Right? We can add two vectors by the method of parallelograms. Right? Let us see how that is possible. The method is very, very similar to triangle, but with a small difference. So again, for reference purpose, maybe I'll use the same paper so I'm able to show the difference over here. Let us once again draw F1. Right? So I'm talking about the method of parallelogram. So what I do is I'll once again show force F1, this is 5 Newton. Now in parallelogram method, what we do is we draw the second vector from the starting point. In triangle, we draw the vectors one after the other. Here what we do is we have a common point from where we draw both the vectors. So this would represent vector F2. Right? So this is F1 and F2. Now what I do is I draw a parallelogram, or I complete a parallelogram. Right? So what I'll do is I'll draw a line parallel to vector F1, right? So this is a line which I've drawn parallel. Similarly, I'll draw a line parallel to vector 2. So this will be the line parallel to vector, and I complete this parallelogram. Now, the diagonal of the parallelogram, which I start from the origin, from this particular point, right, would represent the resultant. So the resultant would be this. Right? Resultant would be the diagonal which starts from this common point through which we had drawn these two vectors. So this represents R. And you can again very clearly see that R looks very, very similar, right? In fact, it would be exactly the same, right? Even with whether you use the method of triangle or whether you use the method of parallelogram. Once again, note the difference. Here you draw the vectors one after the other in sequence, whereas here you have a common point from which you draw both the vectors, complete or create a parallelogram, and then draw the diagonal which will give you the resultant. You can use either of the two methods, right, to find out the resultant of two vectors. Okay, now let us talk about a situation wherein we have more than two vectors. For example, you could have an object again like this, and there could be number of forces acting on this, F1, F2, F3, F4, so on and so forth, right, of various magnitudes, right? Some of them very small in magnitude, some of them very large in magnitude. Now, how do I find out the resultant of all these forces? The method is very simple. It is an extension of the method of triangle. So what I do is I first draw vector F1. Right? I take care of its direction and its magnitude. Then I draw vector F2 from this point, and then I draw vector F3 again. So I draw all these vectors in sequence one after the other, and this is vector F4. This is F4, this is F3, this is F2 and F1. and again this is the starting point, this is the finish point. So this particular line, right, from the starting point to the finish point, right, this would represent the resultant R, right. So this is how we would use a method of polygon of vectors to complete to find out the resultant when we have more than one forces coming into play, right. The last and final point that I want to mention over here is that if while drawing the forces, for example, we have various forces acting on it, right? Let us say we have force F1, F2, then F3, F4, and let us say this force F5. This is F5, F4, F3, F2, and F1. And while drawing these vectors one after the other, if the polygon gets completed, then we cannot draw a resultant, or there is no possibility of a resultant. In such a case, we say resultant R is equal to 0. That means the net effect of this particular vector quantity is 0. That means for example, if these are forces, then the net force acting on this object would be 0. Right? That would happen in case the polygon gets closed. This would also be applicable if we have a triangle. For example, we have force F1, right? And the second force is exactly the same magnitude but in the opposite direction. Then the second force would go in the opposite direction and exactly end over here. And in this case, R would be 0 because there is no possibility of drawing R over here because these two vectors are exactly overlapping onto each other. So in such a case, we say the resultant is 0. Right. In this, with this, I have talked in detail about how to add vectors and properties of vectors. Right. Maybe lastly, I would like to mention one more property, which is the associative property of addition of vectors, which says that A plus B plus C is equal to A plus B plus C. That means in whatever sequence I add, whether I add first B plus C, get the resultant of these two and I added the resultant to A, or I first get the resultant of A plus B and then add to vector C, I would still get the same result. This is one more property of addition of vectors. Okay, with this we have completed addition of vectors. In the next video we will look at subtraction of vectors and find out the methods that we can use to subtract two vectors. Thank you.